Hello and welcome back to STEM Online Academy. My name is Jason Masterakos, for those of you who don't know me. All right, so in today's video, we're going to talk about Gaussian integrals um, from a geometric perspective. For those of you who haven't seen Gaussian integrals before, this will be a new time, your first time looking at them. So, what this YouTube video is going to be about, right, is going to fix one of the biggest misconceptions in applied mathematics and physics, build a structural a way of thinking when it comes to evaluating these integrals, naturally pushing viewers to think in a problem-solving way. And I'll also talk about the applications when it comes to the uh, when it comes to this type of integral, specifically in um, QM probability and stuff like that. All right, so let's get to it, right? So what we're going to do, right, is that there's a moment in every student's education where Gaussian integrals stop being optional, right? Especially if you're in things like if you're a major in mathematics, physics, or engineering, you will encounter a Gaussian integral, whether you like it or not. So it's very important to understand how they work. They show up in probability. They show up in statistical and in statistics. They show in up in QM, quantum mechanics. They show in signal processing. And the thing is, most students deal with them by just memorizing one formula, hoping it fits. There's no value in that. That won't help you at all. Okay. Today, I'm going to do exactly the opposite, right? We're going to understand why Gaussian integrals work, right? The key thing here is the why Gaussian integrals work and why they behave the way they do, okay? And how to evaluate harder ones without memorizing anything, okay? Regardless of what they throw at you, right? You should be able to analyze a Gaussian integral, be able to solve it, okay? So let's get right to it. I'm going to write down an example of a Gaussian integral. Okay, so let's look at one. Okay, so let's say definition here. So definition, DE, just 1 second here, DEFN of a Gaussian integral. Okay, this is how they usually look like. Okay, so as you know, right, let's say capital I is my integral, stands for integral. That's what capital I will represent. Okay, so capital I, all right, and then this is equal to the integral, right? The integral from negative infinity to infinity, okay, of e to the negative ax squared, right? E to the negative ax squared power times dx. Okay, that's what we're going to be looking at. All right. Now, most students are just told that this equals to root pi over a. Okay. Okay, yes, it does equal to root pi over a. This is true. Okay, so this is equal to root, this is equal to root pi, all under the square root of pi over a. Okay, there's nothing wrong with that. That's a true statement. However, though, that advice, if you just memorize it, collapses the moment the integrand changes even slightly. Okay, so if the integrand, when I mean integrand, I mean the function, this here, okay? If that function changes even slightly, memorizing this result will be completely useless, okay? So my best advice for this is to understand how Gaussian integrals work. So for example, if they gave you a problem like this, right? So here's an example. Right? If you have this integral, for instance, okay, so let's say we had to solve something like this now. I'm going to solve an integral from minus infinity to infinity, okay, of x squared e to the negative ax squared power, okay. dx, all right? All of a sudden, guess what happens? Most people are going to panic. Okay, when they see that, it's going to be a problem because they only know the standard form, right? You only know the standard form, this guy right here, right? That would be a problem. As you can see, I've made it more complicated. So just memorizing formulas is useless. I'm not saying they're not important, it's just that memorizing just and then just sticking with that is going to be problematic. Okay, so when it comes to this problem is actually easier than it looks, the one I just pointed out here. Okay, so this guy right here is easier than it looks if you go about it the right way. So you have to go about it the right way. Otherwise, you're just going to go in circles. Okay, as long as you see structure in the problem. Okay, so let me discuss what I mean more generally, what I mean by the structure. Okay, so you'll notice that we have a product of x squared times e to the negative ax squared. If we focus on this part of the integrand, the function, that's what integrand means, this part of the function, okay, it's a bell curve. Okay, so let's look at that. Let's go to a simulation that I created. Okay, so I'm just going to open the media player. As you can see here, we have our function e to the negative ax squared. What type of function is it? It's a bell curve. Okay, the bell curve type function. That's what e to the negative ax squared is. Okay, and if you look carefully, right, not only is it a bell curve, it's normalized. That means that it's a bell curve with a shaded area underneath that bell curve. And that bell curve, as you can see, is centered at the origin being at 0, 0, or the coordinates, okay? All right. So as you can see, the bell curve, right, is completely shaded under that region. Right? Now, this is why I like bringing up models, simulations, and graphs. They don't always give us the answer, but they tell us the behavior of the function that we're looking at. So by doing that, by analyzing the behavior, we can see when we do the algebra afterwards if we're on the right path or not. Okay, so you can see that this bell curve here, right, shaded region underneath. Anyone want to guess what that shaded region is? What the limits of integration would be for the integral if we want to calculate the area? They would range from minus infinity to infinity, right? Because you can see the bell curve goes on forever. If we shade the region of the bell curve, that is boundless. Okay, so it's just going to be going on forever. That's right, the region is shaded infinitesimally. Not infinitesimally, but going on to infinity, minus infinity to infinity. Okay, so as you can see, the y-axis has a density axis. Okay, right, so think of it as a probability, part of a probability density function, and you have your x-axis being x. Okay. Right, so as you can see here, right, it's really interesting, right? So first, symmetry, right? The Gauss. Now, another thing too that's important is the Gaussian an even or odd function? It's an even function. Okay, Gaussian is an even function. Okay, what I mean by that is if you evaluate e to the negative x squared, right, which is let's say equal to f of x, right? If we want to figure out if it's an even function, then f of x has to equal to f of negative x. Okay, so whatever our f of x is, it's to spit out the same output of f of negative x. So if we put in negative x for every x into our equation, right, then it should be e to the x squared over 2 would equal to e to the negative x, e to the negative x over 2 all squared, right? So that still produces a positive exponent because it's an even power, okay? So it's an even function. Odd powers of, now let me tell you another thing. This immediately tells us something, okay? It immediately tells us that odd powers of x will integrate to 0, okay? So if you have odd powers of x, they should be integrating to 0, okay? If they don't integrate to 0, then something is going to be off, okay? So it needs to be integrate, so integrate to 0, okay? And also that the even powers survive. What I mean by that is your your input for your negative x to give you an output as your original f of x function. Okay, that's not a trick. That's just a matter of geometry. Okay, right. Purely a geometric way of explaining, bell curves and Gaussians. Okay, so this single observation, right, already cuts your work in half. Okay, right. So just by analyzing the behavior of the graph of the function, it will speed up, um, your calculation or your computational part of integrating. Okay. All right, so let's get out of this. I think we've seen enough of the simulation or the mathematical model that I have up here. Okay, just give me a moment. I like it too. Hope you guys enjoy it. Let me know after this video if you enjoy these simulations. Try my best. All right. So again, we're just going to see it here. All right, so let's get out of this guy here. Okay. Back to reality. If anyone knows that song, it's very funny. Okay, but yes, we need to get back to reality when it comes to integration. Okay, so let's go to the next page. All right, and I'm going to rewrite this integral again. Okay, so we have this integral right here, right? That we're looking at. I stand for integral as a function of a. Okay, I as a function of a. I as a function of a is equal to the integral from minus infinity to infinity of e negative ax squared e to the negative ax squared dx. Okay, here's the idea students almost never see when it comes to this integral. Instead of asking, how do I integrate, x squared e to the negative ax squared, right? I'm going to explain how we get that x squared times e to the negative ax squared as a product. What happens, you have to ask yourself, this is the question you should be asking. So don't ask, how do I integrate x squared e to the negative ax squared? Ask, what happens when I change the parameter of a? So what happens when I change the parameter of a? Well, there's differentiate. We have to do differentiation under the integral sign. Okay, so we're going to do differentiation under the integral sign. This is something that is not that complicated. Okay, and they should be teaching it to you in your calculus 3 classes at least. I don't know what they're teaching these days in these universities. It's just ridiculous. Schools in general are nonsense. They don't teach you math anymore. That's the first. When it comes to pure math, definitely not. But even the applied mathematics, they're omitting stuff. They're just they don't too many gaps. That's why nobody is able to learn anymore. But then that's what this channel is about: is to closing these gaps, closing the gaps, helping students uh, be 100% solid foundation in their exams, right? And anyone who has last minute problems, not last minute problems, but problems in general in their courses, if they feel that their professor or teacher is not explaining to them, this is the place to be, especially for calculus, uh, ODEs, and also physics as well. I'm also a physics expert. But let's get back to it. I really want to emphasize the issue that we have here. Okay, so how would we integrate something like this? So one way is to use something called differentiation under the integral sign. Okay, so differentiation under the integral sign. The integral sign. differentiation of the integral sign. Okay, so let me explain. If you don't know what this is, very basic approach. Actually, I don't even need to explain the definition. Just watch what I'm doing, okay? So if you look at this, right, so I of A, we have above, right? I differentiate both sides. Pretty self-explanatory. Differentiation on an integral sign means that I have to differentiate both sides. That's the mathematical method, okay? So what I'm going to do is, it's going to be dI, dA, differentiate with respect to the parameter on both sides. This is equal to d by dA of the integral, okay, from minus infinity, okay, so minus infinity to infinity, right? Minus infinity to infinity of e to the negative, let's put over here, e to the negative ax squared, okay, squared dx, okay? And then what ends up happening is that the differential can come inside, right? So inside to the integral. That's what it means by differentiating on an integral sign. So then it becomes integral. So it's better. Okay, so we have integral. I like making my integrals proper. There you go. Minus infinity to infinity. Okay, I have di A of e to the negative ax squared. Okay, dx. Right, we just replace it with a partial derivative with respect to a. Okay, and what ends up happening here is if I differentiate this guy with respect to a, that means x has remained constant, so I'm left with negative x squared. So it's going to be negative the integral, right, from minus infinity to infinity of x squared e to the negative ax squared dx. Okay, this is the entire problem. Okay, so that's my di dA, right? So di dA. Okay, so the integral we want already is appearing naturally with no integration by parts and no guessing. Okay, this is actually going to be faster than doing integration by parts. Okay, actually, if you do integration by parts, it'll just be a nightmare, and you probably still won't be able to integrate because you won't be able to choose an appropriate u in order to get your differential in order to integrate it. So differentiation on the integral sign is probably the best way. So no integration by parts, no integration by parts, and no guessing, as you can see. So it's just a very tight, precise way and clean way of doing this easily. Okay. Now I want to evaluate I of A. So I want to get to I of A. Remember, I have di dA. So that means I have to do something. I have to find its antiderivative. If I have a derivative with respect to A, I need to find its antiderivative. Okay. So that means that I of A I of A. I of A is equal to, right, the double integral, right? Because I now have to integrate, right? If I have di dA, if I want to get to I of A, I have to integrate again. So integrate from minus infinity to infinity, integrate from minus infinity to infinity, x squared e to the negative a x squared dx. Okay? This is what we're dealing with. And it turns out if you were to calculate this, okay, if you were to calculate this bugger right here, okay. Now, for those of you who've taken multivariable calculus, you know how to do a double integral. I'm not going to go through the steps because it takes long, but you should be getting this at the end, okay? should be getting this. Let me just make maybe a different arrow here. So right over here, your capital I of A, right? Right. So I of A. I of A. Use a different color here, actually. So use yellow. I as a function of A is equal to square root of pi over A. Okay. That's what you should be getting, right? So that's what this should be leading you to, right? Root pi over A. Okay. That's my I of A, right? And then after that, what you would want to do, right? The next thing is to differentiate. You want to differentiate, so differentiate right over here. If you were to differentiate, oh, and this is just to show you something interesting here. So differentiate. Or differentiate. There's differentiate. I get my di dA, right? So if I got di dA, so if I differentiate, I get my di dA. What would that give us? Gives us negative 1/2 of root pi, right? Pi times a to the negative 3/2. Okay, that's after we've differentiated I of a. Right, so di dA gives us this. All right, so that's my di dA. And therefore, right, what ends up happening, right, this would imply that the integral from minus infinity to infinity of x squared negative ax squared x squared dx, right? If I were to get back to this, right? Because the IDA, remember what our DIDA was? The IDA was this integral right here. Let me zoom in. This integral right here is my DIDA. So if DIDA is equal to negative the improper integral of x squared e to the negative ax squared dx, and my DIDA was negative 1/2 of root pi times a to the negative 3/2 after differentiating, then my improper integral of x squared e to the negative ax squared dx, since it's equal to DIDA, then this is equal, let me just put it over here, second, I'll use blue, is equal to negative 1/2 square root of pi times a to the negative 3/2. And we have solved our integral, okay? Right? So it's not that hard actually. And this is a very handy technique for calculus students and physics students as well. Okay, I'm going to get into that why it's going to help, why it's such a powerful technique. Okay, so let me just underline this. Okay, so that is what we've gotten as our solution. I'm going to talk about why this method is powerful. Okay, so this method generalizes immediately. So what do I mean by generalize? If you understand this idea, you can compute all sorts of things, right? You can compute higher moments. Higher moments come up in something called probability, mathematical statistics and probability. Very important. Okay. Also multivariable Gaussians. Okay. And quantum expectation values in quantum mechanics. They apply higher moments and expectation values that you learn in probability and statistics classes. So this is really handy. All using the same mathematical method slash logic, I guess you can say. It's mainly a mathematical method, but everything is underlying with reasoning, especially with any form of mathematics. Reason is the foundation of it. Okay, so there's no memorization here. It's just pure structure, pure connecting the dots, and relating one equation to the other, right? And two last things I want to talk about before I get going is the physics connection. Okay, so what do I mean by that? What do I mean? Let's go to the next page. Something called a probability density. Let's look at a probability density. Probability function. 1 second here. My writing is acting weird. It's the whiteboard. Probability function. We'd be saying density function. Okay, let's look at the definition of what I'm talking about here and how it's applied in physics, where it's applied to. So definition. So a probability density function, right, works like this. Let's say you have a probability density function P, where A is a lower bound, small equal to X, which is our independent random variable. You take any probability classes, small equal to B is equal to the integral. Okay, so it's equal to the integral. So 1 sec, I want to make it better. Integral from A to B of f of x dx. Okay, that's a probability density function. That's the definition. Okay. Pretty cool, huh? Okay. So in physics, this integral is not just an abstraction, right? It represents probability distributions, right? Thermal fluctuations, quantum wave functions, all sorts of things. And as I said earlier, with things like bell curves, where normalized, you have a probability density function you're looking at, right? Let me just remind you. Okay, something like this. And you have the bell curve. This is why I like using models, computer models. My curves are bad. My apologies. I have to get better at drawing. That's why I like using mathematical models that have been, programming and stuff like that, because they're, all right, let me do it again. Centered at 0, 0. This is an example of probability density function, okay, with a shaded region, area A here. Area A, okay. All right, so we've got that. All right, and let me see if there's anything else we need to discuss. Oh yes, also, when you compute an expectation value like x squared, expectation. When you compute an expectation value, for instance, like this. This is the exact calculation that you're going to be doing, right? Using this guy right here. So if Gaussian integrals feel mysterious, missing the meaning, you're just missing the meaning, right? not the math, right? So if Gaussian integrals feel mysterious, you're missing the meaning and not the math, right? When I mean math, I mean like the computational part. That's not that important. That's what a lot of people understand about mathematics. Whether it's pure math, applied math, real, doesn't matter what you call it. You need to understand it. You need to understand the meaning, okay? All right, so last thing is common mistakes. So common mistakes, common mistakes that students have, okay? And when I mean this, I mean common exam mistakes. Okay, this is common exam. But here are the mistakes that cost students points, okay? So let me just put, this costs students a lot of points, right? Big blunders, I can say big, or big mistakes. Big mistakes, okay? Number one, trying integration by parts immediately. Don't do this. Integration by parts immediately. Immediately. Don't do this. Okay, please do not do that. If you do that, if your first instinct is to use integration by parts, a lot of problems, you will fail. Okay, I repeat, if you use integration by parts, right, uh, on any complicated integral all the time, you're going to have a problem on your exams. Okay. Number two is forgetting the symmetry. Okay, forgetting symmetry. And number three, yeah, I mean, forget. That's why I brought up that model earlier, right? And also I showed you the graph, same graph of the bell curve showing the symmetry at 0, 0, right? That's a symmetric function and the symmetry properties that it has, very important. And three, finally, memorizing. Memorizing. Memorizing formulas without knowing where they come from. Very big mistake. And you're doing yourself a disservice, right? You need to know how the formulas get there, right? Right? You need to know how to derive them. You need to know how to prove them. You need to know all of that. Okay. Uh, don't just memorize a formula and take it the way it is, right? Scrutinize it and try to try your best to understand where it comes from. Okay. And if you understand the other things, right, like if you understand conceptually, you will be able to derive where it comes from. Okay? It's very important to have number 1, 2, and 3, right? Make sure you integrate that into your study methods for calculus. Pun, integrate. That was supposed to be funny. Okay. All right. So in the next video, since we're done right now, we'll talk about a very interesting integral. Okay. This is going to be purely an application problem. Okay. It has to do with electricity and magnetism. okay, in physics. So that will be very interesting. And we're going to evaluate that integral. Um, we're going to evaluate that integral. We're going to see how it works geometrically in terms of, as I said, electricity and magnetism. Again, I just want to mention something here. Okay, we're going to look at that. One last thing I want to discuss. One last thing I want to say here that's very important. Okay, is that my book, Advanced Integration Techniques, is built entirely around ideas like this. Okay? Ideas that I've mentioned above, common exam mistakes, wanting to upskill yourself in terms of your mathematical problem solving, right? Especially in your applied mathematics classes that lots of students take, especially if you're a math, physics, or engineering student, right? All these concepts, right? All these concepts, okay? All of them, right? All of them can be found in my book, Advanced Integration Techniques, built entirely around ideas like this, using parameters, using symmetry and structure to simplify hard integrals, okay? And if you want one-on-one help learning how to think this way for calculus, differential equations, or physics, you will find tutoring details in the description of in the link below. Okay. All right. So again, both the links to my book and or my tutoring or slash coaching sessions will be in the link below. Okay, in the description. So again, in this video, as I mentioned, we'll take this one step further. Right. In the next video, we're going to be looking at a very interesting integral. Okay, has to do with electric fields. So I hope you guys will participate in that. Okay. At least watch my videos. I'm gonna go back to live shows. I'm just trying to figure out when it's gonna be Wednesdays again at 8 o'clock, 8:30 or something like that. It's 8 o'clock, 8 p.m. Eastern, sorry. So Wednesdays, 8 p.m. Eastern will be a live show. Um, but yeah, stay tuned. I hope this today helped, right? If it did, like and subscribe, and I will see you next time. Have a great day, guys. Bye bye.